So let's identify the Newton's pairs here. We know one of them. I'll put red X's on them. That's A pushing on B and B pushing back on A. Those two are a Newton's pair. And is there any other Newton's pair there? Anything else? Any other interactions that we're catching here? That's the only one. And the reason that's the only one is that it's an interaction between two objects, a Newton's pair. So we only have two free body diagrams here, object B and object A. So what can we have as a pair is A pushing on B and B pushing on A. If I had a free body diagram for the Earth and I showed the gravitational force on the Earth from B, then I could have a Newton's pair with the weight of B on the Earth and the force on the Earth from B, right? Because the book, or whatever this is, the block is pulling on the Earth just as much as the Earth is pulling on the block. Okay, they're interacting. But I don't have a free body diagram for the Earth, so I can't have a Newton's pair identified here. It has to be an interaction between two different objects. The question is, could you have more than one pair of more than one Newton's pair in a free body if you only have two objects? So let's think about this case. We have, this is sort of an aside here. We have object A and object B sitting on top of it. And we're pulling object A to the right. There has to be some acceleration in this case. So we're applying, let's make this surface frictionless. But this surface has friction. And we're pulling with some force F. So in this case, should we draw the free body diagrams? Let's do it. Free body diagram for block B. There's no slipping. Block B and block A are moving together. Let's do B first. B is a little easier, right? What's touching block B? A. A, that's a surface. It's a surface interacting with block B. It can interact two ways, through a normal force on B from A, and through a friction force. What direction is the friction force? Block B is moving to the right. So you're used to the fact that friction is going to oppose that motion, right? But this is a little different. What would happen if there was no friction between those two blocks? We pull block A to the right. What happens to block B? It stays right where it is, and it falls to the ground after A slides out from underneath it, right? We all agree with that? Okay. Now, what direction is the friction force on B? I'll say it one more time. If there's no friction, A goes to the right, B stays right where it is, falls to the ground. What's happening in this case? There is friction here. What's happening? It's staying with A, as A goes to the right. So what direction does that force have to be? Has to be to the right, or it wouldn't go that way. A is trying to get out from underneath it, but it's dragging B with it, so the friction force on B is to the right. This is a little more complicated than I wanted to hit today, but we were going to get there eventually. So that's a friction force on B from A, I guess we'll call it. So that's the only thing that's touching B is A, and we've got accounted for the normal force, we've accounted for the friction force. The only thing that can reach in from a distance is gravity. So let's put that here. The weight acting on B from the Earth. And that's everything. A. What's touching block A? The ground is. The ground can interact through a normal force or a friction force. So in this case, there's no friction on the ground, so there's only a normal force on A from the ground. All right, what else is touching block A? Block B. Block B can interact through a normal force and a friction force. What direction is the normal force? Down, right? The surface from B can't pull on A. It can only push, right? A surface can't pull on something. So B is pushing down on A. That's a normal force on A from B. And there's a friction force between B and A. Is it helping A go, or is it hurting it? Is it preventing it from going? A is trying to go to the right, and as it goes to the right, it rubs against B and pulls B in this direction. And what is B doing to A? It's rubbing in the opposite direction. Right? So A is trying to slide out from underneath it, but there's a friction force that's not letting it. So the friction force is in the opposite direction. That's the friction force on A from B. And those are, another way to think of it is as a Newton's pair. Those are two objects interacting with each other. A and B are two objects that are interacting with each other. And so the forces that they produce in that interaction have to be equal and opposite, equal in magnitude, opposite in direction. Let me finish block A. So we've got the ground, we've got block B. There's one more thing touching block A. This pulling force, right? And then we have gravity reaching in, right? And that's everything. That's our complete free body diagram. So now we can identify Newton's pairs. There's one, the normal force on B due to A, and the normal force on A due to B. That's a Newton's pair. And there's another one, the friction force on B due to A, and the friction force on A due to B. So if we pull with a little less force and A doesn't move as fast to the right, doesn't accelerate as quickly to the right, then the friction force on B becomes a little bit less, and the friction force on A also becomes a little bit less. If we stop pulling on A, what happens to the friction force between A and B? Goes to zero. Goes to zero, because then there's no horizontal force on A, and there would be no horizontal force needed on B. All right, so those two are linked, right? When one of them increases, the other one increases. When one decreases, the other one. They're always going to be equal and opposite because they're an interaction between those two objects. So this is an example where we could have two.